So it was, we had the resistor in series with FCAM. Thank you. Resistance. Inductor. 150 millihenries. I assume this is with my corrected numbers.
Yes. Yeah, if you see the, I think the capacitor was the one where we had to correct the numbers,
Okay.
and so that's why it's got white out over it.
Just like two numbers.
Yeah, it was just, I think just two.
All right, so we had X of C equal to 79.58 ohms, and X of L equal to 47.12 ohms. Frequency of 50 hertz, which meant that our angular frequency is 314.159 radians per second. Right, we're on the verge of finding C.
Yes, we're gonna work on it.
We had talked about our E squared, well, epsilon squared, VR squared plus VLC squared, and we had our crazy.
All right, so let's get the phasor diagram. So I put, this would be the current, no, not current. This is the voltage of L, which is the voltage across C, which is the voltage of what I'll just label as LC. The current phasor, let's see, ice, so for capacitor, current comes first. And then inductor lags. And we established that IL is bigger than IC.
Which meant that our IR, or I epsilon, which equals IL minus IC, was like,
And that would be, since the sum of those two would be equal to IR. And so VR would have to be in phase with that. And we used to have other colors. So we had V on the outside VR, and then I added these two. And I think it was a little bit above the line yesterday, but
Yeah.
you know, unless we crank through the math, we really don't know exactly where things are. All right, so to get the EMF here of the power supply, which I guess I should put the label over here. We had to use Pythagorean theorem, so we know that VR squared plus VLC squared equals epsilon squared. Now I know that the current across the resistor is not the same as the current flowing across the inductor or the capacitors. It's across the sum. So but we'll use the Ohm's law bits. So that's I across the resistor times the resistance squared plus the current flowing across here. So we need to figure out what VLC is. So I'm going to create sort of a new function here. This is the current flowing across LC times XLC. This is not really, it's a temporary variable right there. Because, yeah, the capacitive, inductive reactance, I'm making up words here. Combination of words. The words themselves were legitimate. Oh, equals I power supply times the impedance squared. Let's make sure I am actually heading towards that. All right, so let's try to figure out what we know, how we go about this. I know that the voltage from here to here is the same. I know that VL equals VC, as is indicated over there. I know the voltage across L has got to be the current going across L times X sub L. So, and that has to be equal to IC XC. I actually know what these numbers are. I have some relative value here. I know that IL is equal to XC over XL times IC. That's an L there. That's a C there. That's some ratio here. We have the numbers right there, so whatever that is. I know the current flowing across, flowing basically into here has to be IR. So let's match up the things that we actually do know here. Which equals IBS. Because whatever current's flowing out of the power supply has got to flow across the resistor. There's no junction in between them, so they are in series. So ILC, we know ILC is equal to, as we have over there, IL minus IC. I don't really need to change the way I make my C's, they too often like L's. IL is equal to VL over XL minus VC over XC. Well, VL and VC are the same thing, so that's just VLC times 1 over XL minus 1 over XC. So we can take this now and actually plug that into here. No, I lied. We take that. Let's see, equals, oh. That's back up there. So VLC equals ILC times XLC. That we know is IL minus IC. Well, that we know is VLC times 1 over XL minus 1 over XC times XLC. And so therefore, I have VLC on both sides. one over here. And so I have XLC equal to 1 over x sub L minus 1 over x sub C to the negative 1. So where I want to go with this.
Why is it to the negative 1?
Because I have 1 equals this times this, and so this, so if I'd have to divide both sides by that.
Okay.
To
I
raise
see.
to the negative 1 just means 1 divided by.
So now we could plug in Excel and XC values.
So what we're left with is, if this ILC, which is this right here, this green thing, is the same as IR, which is the same as IPS, then, I forgot to square that. That, and that are all the same thing. Therefore, there we go. So I'm left with R squared equals, not equals, plus XLC squared equals Z squared. R squared plus XLC, I know is that mess over there, 1 over X sub L minus 1 over X sub C squared equals Z squared. Or just take the square root of both sides. Now we'll acknowledge this is one of the harder problems. Coming up with the Phasor diagram, I think is perfectly within scope. This is a little bit of a stretch. Coming up with this relationship definitely is doable. Knowing and that. Just to separate those who really know what's going on with those who don't. And then the rest of it is, you play around with it until it works. Not everyone's mind is in that sort of mindset with taking a test.
So we would just plug and shove to solve the Z now, because we have one value.
Yeah, so now, so I have 100 squared. So Z equals the square root of 100 plus 1 over X sub L, which is 47.12, minus 1 over 79.5 squared. We came right through it and end up with 4. It won't be that. It's gotta be at least 3. So it's roughly 0.5 minus.
Okay.
107. Let's see what it is. It's either somewhere around 107 is my guess, or 302. I'm having an issue with it.
I got 152.
Or 152.
0.79.
152.79.
Apparently, am I doing that in my head? I'm not particularly good at it. So 152.75?
9, not 75.
That's beautiful.
Gorgeous.
Units?
Oh.
Yeah, there we go. Fun with AC. And the rest is just various combinations of R, L, and C. Yeah, you can stick more than one resistor in there, more than one inductor, or it doesn't really. Let's just do one more, we'll just set up the phasor diagram, we're not gonna do any of the analytics. Just for the practice. And then we will get into some relativity to make you question.
Everything we think we know.
Yep. I might have said this before, and I apologize if I have. When I was, my first year of teaching, I was teaching high school, and a student said, when you first start out, they teach you what? Then they teach you what and how. Then what, how, and why. And then they run out of things to teach you, so they teach you to question everything you've ever been or taught. So, relativity is the point where I teach you to question everything you've ever been taught. All right, phasor diagram. C, R, L. That is a sad line. So what is the first off, how many phasors will there be?
8.
All right. And what phasor should we start with?
Well, I guess we would have to do the series of RC.
All right, so they're in series, what's gonna be the same for them?
They're in series of current, is it?
Yes. So we'll start out with the current. And in my traditional 30-ish degree angle. So this is IR equals IC equals IRC if you want, but there's two of them. Now what?
Yeah, because for a capacitor, for a capacitor, current leads by 90 degrees, right?
All right, so so voltages, I think that's what Laura was going for.
Mm-hmm.
All right, so that's VC. All right. And what about VR?
Shouldn't it be in phase with IR?
It should be.
Okay.
What about the inductor? Voltage or current?
It would be, it should be voltage, right, because it's in parallel.
Yeah. So the sum of these two. That would be the voltage of the inductor. So we have a mathematical relationship here between the voltages that VR squared plus VC squared equals VL squared. So I'm missing three phasors.
We have the voltage for the inductor and the current, no, the voltage leads by 90 degrees, right, for an inductor. So we can get the current phasor.
Alright, so the current phasor is which quadrant?
Should be lagging by 90 degrees,
Okay,
so it should be in third quadrant.
Yes.
Okay.
alright. So we got the current there, so that is a right angle there. And that's V, not V,